Yeah, so today I'm going to talk about like how we can do comparisons of language models, especially LLMs as well. So as we know that most of the language models have like the problem with overparameterization, and the basic need why we need comparison of doing language models comparison is basically, so first initially when attention-based model like or even so this is different from comparing deep neural networks. So this is not kind of like so there's like comparison technique in neural network as well. So, of course, that like pruning or quantisation. So we also use that into word embedding comparison as well. But here I'm only going to cover how we do comparisons of word embeddings in language model. So as you can see that the BERT-based model is like the base model is like 110 million to and the BERT large goes to like 350 million or 340 million hour, and the size grows like 1.5 gigabytes. So you can see that, and for like Roberta was also benchmarked on like multilingual as well, like as a master language model. So this has also quite a large parameter and has a tendency to not tendency, but is more likely to prone to overparameterization. In terms of why, like what are the key issues in language models, like these big language models? So basically, it requires like a lot of computations, especially CPU, when you kind of like load or like if you have to keep artifacts like a fine-tuned version of your LM or language model. So, and if you have to deploy on like mobile devices, let's say using maybe we have like quite many frameworks like standard TensorFlow Lite to deploy language models on phone to especially for image recognition or face recognition kind of stuff. So we there they use a lot of comparison technique to do that. In language model, we do have like especially for researcher or a student, we can't like kind of reproduce or even at a company level or at industry level, we they actually kind of like not just use the exact maybe these big models, they may be kind of like compress as well. So to keep the less energy consumption of memory footprint. So the goal is to like make a like less memory footprint of these language models and to make fast and also see, comparative performance in terms of like on NLP or R tasks. And we actually know that in the literature we have like lots of technique to compress, and few of them are like mainly used in compressing neural network as well, deep neural network. So these are weight sharing. So weight sharing is like how you can share weight within maybe fully connected neural network. So it's similar analogy also used in embedding as well. So in embedding, you kind of like share the word, these vocabularies, so you make it identical instead of like keeping it quite sparse. So you can also use the analogy of weight sharing in from neural network literature in word embedding as well. So in this today's talk, I'm only focusing on first two methods because I think most of the like industry grade goes into quantization or distillation. So, but I'll tell more about it, but I'll not go one by one in here. So in pruning, we know that so this is like a 3-layer neural fully connected neural network. So you can see that in the first diagram, it actually shares. So each neuron in each layer will actually share in the next layer, but once we apply the pruning approach, we can actually only share all the previous neurons information to the next. So it will be like one-to-one, more like so inverse bijective kind of stuff. So it's like you're not like so pruning is how you can kind of retain the single information, but not keeping like more memory. So because here you have like three, so you're feeding information from each neuron in the layer in this layer. So and it has like this layer reversal as well here. So you can perform layer reversal after that to compress even more after this pruning. And as I said that it of course has a like if these days like we actually like lots of researchers support like sustainability and like if you kind of compute down to parameters and like kind of goes to costing like pricing at unit economics like how much cost. So let's say Roberta. So Roberta has been no BERT. So BERT has been used like so they use like 64 V100 GPU to actually kind of retain the original BERT, and we saw like almost like the carbon footprints that accounts for a passenger flying from San Francisco to New York. So it's quite large. So that's also another motivation why we need to kind of like also reduce the memory footprint of language models. As you can see that in this figure, so this is also from literature, I think 2016 paper. So here they in pruning you do by neuron. So yeah, you kind of like have to perform like, so these are the records that this paper has done that they perform this beat operations. So beat operations, like they recorded all the like neuron by neuron in each layer. So they have this energy in joule and also this relative cost in dollars. So it's a lot of like memory. Just so you can see that this is like just a simple pruning. So its computation is too large if your retaining data is like that much substantial that original BERT was trained on. So in here, so this is like a recent work. So I'm going to introduce my work. So this is like a work from CCAM 2023. So what we did is like, so we actually took the original embedding to kind of like partitions, and we have like partition approach already in literature, but the difference here is like we kind of perform mapping, and we perform mapping. So we perform some sort of like linear projection, so linear transformation kind of stuff. I'll introduce more what's the actual algorithm that we are using to actually present to perform lower dimensional representation of embedding after partition. So the main issue is like the main highlight of this work is like we actually use Cartesian product. I mean, it's quite simple these days, but we still able to. So for this work, we actually benchmarked like compressed down and also looked at the comparison rate of BERT, Roberta as well. We looked at the multilingual, but multilingual is not very good on like apart from English, Spanish, and German. So so we used Cartesian product, and also we use this recent. I think so. There's a like a algorithm that's called GGIP. So so there was like I think a few months. So it is something similar, but it's not that. So we use like clustering algorithm as well, k-means, to kind of optimize the auto vocabulary problem in mixed language models. So our focus here is like only on those models which are like not just next sentence prediction, but also mixed language models. So, and we do have like comparison rates around 99.8 to 99.9% most on glue benchmark. So on the left-hand side, this is like original language model, and this, different colors. So it's called LMNPQ that I kind of like symbolized those. So it is like different eight. So these are like, let's say you're feeding some words or sentences. I mean, it can be word or sentences longer as well. And so this language model right here is like your original language model. Now what we do is like we kind of split each tokens, like when we when we make the embedding of each sentences after you input to the original embedding, so we kind of like split, and this is like symbol like partition. So after we split this, you can see like we do have like, so we have like eight different tokens here. and we split like 4, 2, and in a way like, so you can see like it's 4 and 4 and then like 2 and 2. So there's like there's a formula that we kind of like, but this is like just for to show a generic case like how the actual partitioning will happen. So after we partition the embedding after after we get into the language model, so we partition it, and then what we do is like we perform linear transformation across. So after we get this splits, we perform mapping, and we do not use all these splitted partition embeddings. Actually, we only use that one from these 4 splits. Like you can see, there's 4. One from each split that it can share the information. So we also kind of like solve the solve the problem of auto vocabulary as well. So this is something like you can think of like a foundation to the word embedding as well. Like I mean, at least from GLOVE maybe, or the character based language models. So the main analogy, I think I can get down here. So you can see that we do have like a partitioning condition, and this is like, I think basic. I think you can be able to see into the some quantization technique of like to compress a word embedding. But the uniqueness here is like we perform mapping across those splits, and once we do the split, we call it subspace embeddings instead of partition embedding, because we're performing linear transformation across different tokens, not within the split actually. So, and we generalize it via a formula through Cartesian product, the basic Cartesian product, and this like code book and word embedding tables we create with. So we do have these many embedding tables. So D by F is your so D is your dimension. F times you kind of like iterate, like depends on like how many splits you'll have. And the subspace embedding will be the dot product operation as well. So this is like this subspace embedding we apply on pre-trained language model, and we kind of like, as I said, that the subspace embedding is different from literature that you see. I think is found goes by subspace learning. So subspace learning is slightly different. So it kind of learn the each embedding or each like layer in a neural network, but it doesn't like perform projection to kind of compose the information from both. What we're doing here is like we kind of retain after even a splitting or partitioning the embedding, and we use like 2 algorithms. So first is like we perform modulo operation to actually sequentially allocate the tokens in a split, in a embedding splits. And also the second approach is like we performing randomization as well on the, because we don't want that problem of like overfitting as well, because if you're sharing too much during the fine-tuning stage, I think it will be kind of like your model is like kind of exposed to external information. So this is like a dispersed subspace embedding approach. So this is the first, as you can see that in the very first, we kind of like created an embedding table. So we have like after having each splits the subspace embedding, and we initialize that, and we kind of like reiterate on each split, and at the end we get the compositional function that can actually, that's a concatenation operation in a way. So in the end we get a compressed embedding models in a way of and these are like embedding vectors. As you can see there, these are like neural language models that we use. So the very first one is like we apply so this S that you see is a subscribed Roberta, so you can think like that. So these are the so we reduce, so this column is like reduced size of our approach. So this is your original Roberta, and we applied actually the subspace embedding. Now the 51 million goes down to like almost 50, 58, 59, 54, 55 percent. And this +2 means like these many splits we did. So 2 split, 3 split. So that kind of, so, and we kind of like increase to see like if we kind of increasing, because let's say if you're just putting like 2 words in as an input and you're making a large splits, I think it won't make sense. But we kind of like try to see up to 8 different subspace splits to see that how the performance goes. So this is actually just the like compressing down. So I mean this can go worse, like when you do +8. And we also did for the extra large as well. So you can see that we kind of like, this doesn't like you can see like, I mean it doesn't compress much, so it's like 128 million only. So the second is approach that we do is like we randomization. So we kind of cluster similar tokens as well after creating a split, and then we perform this subspace learning operation. So for that, we, of course, this k-means is like to operate to group the similar splits, and then you perform projection. So we find like what are those random candidates among the splits after we perform the projection. So now you can see that we kind of like applied on most of the data set on the glue benchmark. So this is so if here is like the number of splits, by the way, and these are the vocabulary size. So sorry, the yeah. So the F is like, this is what we are splitting actually. So this is the original one, you can see. And you can see that we only get competitives on. So this is the original, by the way. This is ours. Once we apply only single split, so single split like you just perform once, and this like you kind of like incrementally make a split. But when we go like beyond like I think 4, I think it started to get worse, because I think the approach that we are trying to do is because we're making very low dimensional representation of each token. So because of the split, so it doesn't. So in here we only fine tune. We doesn't pretune, because it's, if we make a split, it like it is too computationally extensive. So we does now what we're trying to do is like we're trying to kind of like use this as a tokenizer, like a new because it's a compressed model, so we can use this as a tokenizer to apply to perform pre-training basically. So and this is from the second algorithm. When we perform clustering, the clustering works even better because of the randomization involved, and it doesn't like kind of like expose to similar tokens when we perform splits. And these are the compression rate in the very third column. Yeah, this column. So you can see the compression rate is quite good. And also on SST, we do get this very competitive. So it kind of like outperform even. So this is, but this is like because we're using like Roberta and BERT in a way. So so this for Roberta English. Also, I think on some of the like comprehension data set, or like you're doing like reading comprehension, or how do I say, not, yeah, question answering as well. I think it doesn't like outperform, of course, because we compress this approach is like compressing too much parameters. So that might be a slight drawback. But yeah, we haven't performed pretaining of using this tokenizer. Now what I'm doing at the moment is like, so these days, so this is my recent work, but I'm not like revealing all the information. This is like just a highlight. So now what I'm trying to do is like you feed an LLM, And it is similar like question answering. So you feed the LLM and you put some. So you have this pruning unit of your, as in the very first diagram. So you have the LLM. You kind of like make a splits. You can think of like transformer, and then you have like these parameters sitting at like maybe the feed forward layer or the multi-head Hanson, and even the embedding. So what we're trying to do is like we're trying to make an approach that you can feed into like context level pruning via prompt. So you kind of like ask the prompt to do some instruction. I mean, it's it's more like, but what we're trying to do is like not like a single word, but you can actually comprehensively give like maybe 30 character long or maybe 40 character long. And you can actually ask like perform pruning, quantisation, or even like recent state of the art like methods. So now we're trying to do the other way around. Like now we're trying to not let the user to do engineering, but the LLM will do the engineering. So this is like this will be your input interface and in the input. So this is like instruction you kind of like provide, and you'll feed input. So input will be like what you want to like compress. Do you want to like in this figure? Do you want to compress all these units or just single unit, or maybe you want to prune or you want to kind of compress just one of the layer. More interactive, like not the user do all the engineering. In the end, what we're doing is like after it compress in the backend, we only storing artifact. So we have the snapshot, not the actual memory footprint of that compressed language model. So and we're taking that artifact like as a snapshot. So we're kind of like reducing a lot. So we're using like, so I'm using at the moment is like this Milvus, this Agilist vector DB to kind of like process the this artifact because it's a quite simple when a user does, but in the backend it's a lot of consumption. So now I apply this method in the like at least on the line. So and it's computationally very extensive. We're doing comparison, but experimentally it's very expensive. But somehow what we're trying to do is like we're trying to also see like how fast we can compress down as well. So not just looking at the compression rate, but also performance plus how fast it can perform as compared to existing. So we kind of record the time as well. So on the Llama 7 billion, so these are the reduced one. So we kind of like compress down to 5.4, 5 and 4.5 and even lesser, but when it goes to 2.5, it doesn't perform better. So so you can see that it is, the sparse GPT, these are like at the moment they are like at the current state of the art, but ours is like last one, this 4 compressor calling. Sorry, so I'm not revealing the actual technique, like how the pipeline works, because it's still in work in progress. So this compressor, you can see the difference is quite large. So even with compressing, we get a very competitive performance on these data sets, and we also kind of like averaging to see. So averaging is like we performing like number of multiple folds, like 5, 7. But as I said, it is very computationally extensive. So we need to adapt like some other metrics to see like is it. But we use like a standard metric for reading comprehension task. I think yeah. So so the takeaway would be like that we introduced like a compact embedding structure that there is the subspace embedding to reduce the number of parameters in Python mass language model. I say neural language model, but actually it's a mass language model, sorry. And now what we're trying to do is like we're trying to like kind of like scale this operation to actual like the current state of LLMs. In the previous this work in progress, the llama carries of course a lot of parameters. So but yeah, we kind of like not using this subspace embedding. As I said, that retaining is like quite expensive. So we're looking at other ways to kind of like reduce the computations. As I said, that we tested on the glue benchmark, and also we kind of like we don't have like a competitive performance apart from English or Spanish language. And we at the moment we exploring some so there are like new derivatives of XLM as well. That's is very recent, I think, is. And also we do have I think in information retrieval or like text summarization task, we do have this FLAN T5. So FLAN T, so we kind of like applying to those as well, because those are like very recent lamps too, and those are like of course state of the art for summarization task, or even for ranking as well. So we kind of looking to apply this subspace embedding on compressing down to FLAN T5 and testing checking the performance, whether it like is getting competitive or not. So to see its effectiveness of this approach. Thank you.